Okay, so let us start today's class. And since we have had a small gap, I was thinking of just going over the laws of radiation, the three laws that we had discussed before we continue with the next ones. So the first thing that we had talked about was the Planck's law. Planck's law essentially gave us the emissive power of a black body. Just hold on, let me get my pointer around. Okay, so this is the emissive power of a black body, and it gives us a function or give us the distribution of this emissive power. It's a one parameter distribution. And what is the parameter that it depends on? The parameter that it depends on is the temperature. It is a one parameter distribution function of the monochromatic emissive power as a function of radiation, a function of the wavelength of radiation. So it is a function of lambda, and you're getting the emissive power as a function of lambda, and only other single variable that is there is equal to the temperature. So at different values of temperature, as I change the wavelength, how does the emissive power of a black body change? This is given by Planck's law. And we had already discussed what for each of these terms of the Planck's law was. So if you look at the constants, if you just leave out the constants K1 and K2, the other terms that were there was lambda and temperature, which is out here. Now, based on this, what we went to next was to looking at this figure. This is essentially the Planck's law plotted. That means on the y-axis, what we have is the emissive power of the black body. On the x-axis, we have the wavelength. And each of these lines are drawn at different temperatures. So this is drawn at a particular single temperature. As the wavelength increases, how the emissive power keeps on changing. So you see that as the temperature increases, for each particular temperature, the emissive power goes through a maxima. It is low, it increases, reaches the peak, and then goes down again. And the position of this peak keeps on decreasing, is at a lower wavelength as the temperature increases. So if I want to describe these these lines or the figure that is out here, we can see a few points, and let us go through these points again. At any temperature, the black body emits radiation covering the entire range of wavelengths. So we have, as the wavelength changes, we have the emissive power going through an increasing value and then comes down again. The emitted radiation is a continuous function and has a maximum. So this is a continuous line. Of course, each one of them has got a maximum peak. At any wavelength, the amount of emitted radiation increases with temperature. So as we increase the temperature, for example, I take a wavelength of say 1 micron, I draw a straight line from here, and the amount of emission radiated at 800 Kelvin is given by this value, which is about 5. And then when I go to a temperature of say 1000 Kelvin, this increases to about say 400. Then I go to about a temperature of 2000. This increases to about 3 or 4 into 10 to the power 5. So as the temperature increases, the amount of emitted radiation also increases. And as the temperature increases, the peaks of the curve also shift to shorter wavelengths. So if I can draw a line through that, this is kind of the through all the peaks which is out there, you will see that there's a decreasing value. And the radiation emitted by the sun, considered to be a black body at 5800 Kelvin, given by this particular line, is maximum around the maxima of this wavelength of this temperature light falls in the visible range. And that is why we can see things because of the sun's radiation. Earth at the temperature of 300 Kelvin emits radiation in the infrared region. So this goes into the infrared region when the Earth starts giving out radiation, because the temperature is much lower for the Earth. How much is the temperature of the Earth? Around 300 Kelvin that we are talking about. Next comes the Wien's displacement law. This Wien's displacement law is based on what we had seen from the Planck's law. From the Planck's law, if I look at this figure, let me just try to increase the size of this. You will see that as the temperature increases, the peak maxima shifts to shorter wavelengths. And that means they are inversely proportional to each other. And if I multiply the peak value wavelength of the peak value to the temperature, this gives you out a value of this many meters per Kelvin. So if I go out now, I can see, or in terms of microns, I can write it as this is equal to 2898 microns Kelvin. That means if I make a multiplication of the peak value of the maxima to the temperature at which the peak value is, it comes out to be a constant number. So if you want to define the Wien's displacement law, it says Wien's displacement law states that the product of wavelength of maximum value of monochromatic radiation and the absolute temperature is a constant. So if I know the value of the temperature, I can find out where my maximum peak is going to be. Or if I know the maximum peak, I can find out at what temperature is this value happening. This is my Wien's displacement law. The next one is my Stephens-Boltzmann's law. The Stephens-Boltzmann's law is an extension of my sort of like Planck's law. If you remember the Planck's law, what we had said, it gives us the total emissive power or the total emission given out by that black body for as a function of wavelength at a particular temperature. So now if I just integrate that value from considering wavelengths of 0 to infinity, what I get is the total emissive power of the black body, which is EB. And so I put in the function of EB lambda, which is for a single wavelength. And if I integrate it from 0 to infinity, what I get is something which is called EB is the total emissive power of a black body is equal to sigma into T to the power 4. Sigma is given as 5.73 into 10 to the power minus 8 watt per meter squared Kelvin to the power 4. And this temperature is the temperature, absolute temperature of the body, always given in the Kelvin scale or the absolute scale. This law helps to calculate the total amount of radiation of all wavelengths, wavelengths of all kinds of wavelengths in all possible directions by a black body. And if that is the case, and if I want to find out a fraction of that wavelength, I can do that also. A fraction of that wavelength is this is the total emission given out by the black body, because we are integrating it from 0 to infinity. And in the numerator, we can integrate it from 0 to a certain wavelength lambda and find out what is the fraction of that emission as compared to the total amount of emission that is given out by the emissive power of the black body. This is my Stephens-Boltzmann's law. So in short, the Stephens-Boltzmann's law is written given as EB, or the total emissive power of the black body, is equal to sigma into T to the power 4. We had done it till here. The next thing we talk about is something which is called the Kirchhoff's law. Now, emissivity of a surface, the emission that is given out by the particular surface because of its temperature, is quite an important property of radiation. So the emissivity of the surface is defined as the ratio of the radiation emitted by the surface to the radiation emitted by a black body. So this is my emissivity, which is epsilon. This is a ratio of the emission of amount of emission given out by any surface by the maximum amount of emission that can be given out. And you know that the maximum emissive power of a black body is equal to what? It's a maximum one. So this is the maximum value that can be given out, and this is what is given out by the actual body. So the emissive power or the emissivity of a body ranges between 0 and 1. The worst possible case is 0, and the best possible case, when it's a black body, this is equal to 1. The emissivity of a real surface varies with the temperature of the surface, the wavelength, and the direction of the emitted radiation, which side it goes to. Now let us understand how we can develop a relationship between absorptivity and emissivity. Now let us look at this figure for this purpose. Look at this. This black outer line, it's an not a fixed shape, it's an unknown kind of a shape that is there. This is an enclosure. This enclosure has got a surface temperature equal to Ts, and this enclosure behaves like a black body. Now the heat flux incident on any surface inside, the amount of heat flux that is incident or given or falling on any body inside this enclosure is given as Q, or small q. A small body of area A1 is present inside the enclosure. Now we place a small body, area of this body is equal to A1, that is present inside my enclosure. Now what is the If E denotes the emissive power, E1 denotes the emissive power of the body. That means E1 means capital E1. And the size of this body, or the area of this body, is capital A1. And absorptivity is equal to alpha 1. You had, if you remember, I had told you that absorptivity is denoted by the letter alpha. And because it is of body 1, I'm calling it alpha 1. So the rate at which the body emits radiation, that means the body gives out radiation because of its temperature, is equal to E1 into A1. What is E1? E1 is the emissive power of the body, and A1 is the area of the body. So the total amount of energy, which is or the rate at which the energy is given out by this body, or the emitted by this body, is E1 into A1. Now this, I told you that this black body has got a surface temperature of Ts, and any kind of heat flux that it gives to all the bodies which are inside this enclosure is small q. So small q into A1 is the area, that is, because q is flux into area, and this is multiplied by my alpha, which is my absorptivity. So this is the rate at which body 1 receives the radiant energy. So on one hand, it receives the radiant energy. On the other hand, it gives out the certain amount of energy. So these are the two things possible. Now, if the body 1 is in thermal equilibrium with the enclosure, what does it mean? It means that the body 1 and the enclosure, both of them are at the same temperature. That means they're in thermal equilibrium. There is no more flow of heat, etc. that is happening. Then the rate of emission is equal to the rate of absorption. There are two possibilities I told you, that the rate at which heat is coming to the body and the rate at which heat is going out of the body. Because they are in thermal equilibrium, these two rates are equal. E1, A1 is equal to alpha 1 Q into A1. So the A1s can be cancelled out from both sides. So this becomes E1 is equal to alpha 1 into the radiant heat flux. Suppose this body, A1 body that is inside this enclosure, is now a black body. So the emissivity, or the emissive power of the body, is given as EB, and the alpha 1, or the absorptivity, is the absorptivity of the black body, which is equal to 1. For a black body, you know, all the radiation that is falling onto it is absorbed. So the absorptivity is 1, nothing is reflected and nothing is transmitted. So this is equal to 1. For a black body, EB is equal to Q. So if I put it in this expression, A1 dono side se cancel ho gaya. E1 is given as EB, and alpha 1 is equal to 1. And so the EB is equal to Q. Now, if I put it in the expression, or divide one by the other, that means we divide this expression of E1 equal to alpha 1 into Q by EB by Q equal to Q, then this is what I get. So E1 by EB is equal to essentially absorptivity, or alpha 1. According to the definition of emissivity, that is, if you remember, we had seen this definition of emissivity. Where did we see this? Let's see here. What was the definition of emissivity? It is the radiation emitted by any body by the radiation emitted by the black body. Now, if I go through here, you will see that this the same thing we are writing out here. The emission by the body 1 by the emission given out by the black body. So this is my definition of emissivity. And if you look at the alpha expression, it comes out to be exactly the same, that it is the emission given out by any body by the emission given out by the black body. So based on this, we can say that epsilon 1, or the emissivity, is equal to the absorptivity. So what does Kirchhoff's law state? Kirchhoff's law states that the emissivity of the body, which is in thermal equilibrium with its surroundings, is equal to its absorptivity. So because we are talking about this body 1, so body 1 was in thermal equilibrium with the surroundings. If this body is in thermal equilibrium with the surroundings, then the emissivity and the absorptivity both are equal to each other. This is given by Kirchhoff's law. Now we have already talked about something which is called the black body. So any real, and we so know that the black body is the one which absorbs all the radiation falling onto the body, and it also has the maximum emissivity, and the emissivity of a black body is equal to 1. That means it can give out the maximum amount of, the emissive power is the maximum amount of heat is given by an ideal black body. And we had also seen that black bodies are not real, it's an idealized situation. So the real substances, they emit less radiation than the ideal black surfaces, and as measured by the emissivity of the material. So emissivity of the material, so if you look at the emissivity again, and let me go back quickly. The emissivity definition says that epsilon 1 is equal to E1 by EB. So now if this body becomes a black body, it becomes EB by EB, and hence your emissivity becomes equal to 1. So any real body is actually has got an emissivity of less than 1, where the numerator is the emissive power of the real surface. Here, the emissivity and absorptivity of real surface may vary with its temperature or wavelength of radiation emitted or absorbed. Here we also define another kind of body, which is called the gray body. It is not a black body, but is a gray body. This is a substance whose emissivity and absorptivity are independent of the wavelength. It does not depend on the wavelength. Whatever the wavelength is, its emissivity and absorptivity remains the same. So gray body is also an ideal body. We don't have a real life gray body. We can find bodies which are close to that, but there's nothing a perfect gray body in reality. It's also an ideal body, but its epsilon and alpha, that means emissivity and absorptivity values, are both less than unity. In case of this was considered for a black body, both these values would have been equal to 1. But by gray body, the value is less than 1, that is less than unity. And for gray bodies, this is epsilon lambda, that means for any particular wavelength is constant, and absorptivity for a wavelength is also constant. So the monochromatic properties are constants over all wavelengths. So the total absorptivity and the total monochromatic absorptivity are equal. So epsilon is the same as epsilon of any particular lambda. There is no variation because of the change in wavelength. Similarly, the absorptivity, the total absorptivity is the equal to the monochromatic absorptivity. So emissivity and absorptivity, both of these remain the same in terms of in case of a gray body. So if you apply Kirchhoff's law to the gray body, if you remember what is Kirchhoff's law said that if a body is in thermal equilibrium with outside, then its emissivity and absorptivity are equal. So based on that, we can write that for any particular wavelength, absorptivity is equal to the emissivity, and if you're talking about the total value also, your absorptivity is equal to the emissivity. So spectral emissivity is defined as the ratio of the intensity of radiation emitted by a body at a wavelength lambda to the radiation emitted by the body at the or by a black body at the same temperature and wavelength. The same thing as the emissivity definition that is there. Now, if you look at this figure, you can understand what the situation is. So if you look at this dotted gray lines out here, this is for a black body. That this is the emissive power increases, reaches a maxima, goes down. And your emissive epsilon, lambda, and epsilon, total epsilon is equal to 1. Now the gray line, which is with the smaller gray dots out here, is for a gray body. Everything is same except that the epsilon values are less than unity. In this case, for example, we are writing an epsilon value of 0.6. And the solid line, the curve which gives the solid line out here, which was almost on the gray body, but not exactly, this is for a real body. A real body can be something like this, with its emissivity less than 0.6, say less than 1, but it is not, the curves are not essentially smooth like what we have for a gray body or a black body. Because these two cases, the black body and the gray body, these are all ideal, but a real body is similar to it, but not exactly the same. Next, we come to another extremely important property which we will use quite a bit. So what have we talked about? We have talked about absorptivity, we have talked about emissivity, we have talked about transmissivity, we have talked about, what else is there? Reflectivity, all of these things, and the emissive power of the body. Here we will talk about the view factor. Now, what is this view factor? Let us see. According to Stephen Boltzmann's law, the energy emitted by a black body is sigma into T to the power 4. If the body is non-black, then there's an emissivity term that comes into it. So emissivity into sigma T to the power 4. For a black body, this emissivity is equal to 1, so we don't need to write that. So we can write overall for a single body emitting radiation, we can write Q by A, that means this is flux, is equal to emissivity into sigma into T to the power 4. However, when we have two surfaces, which are different in terms of, say, temperature and kind of emissivities, say, for example, we have one body like this and another one like this. So the question is that whatever emission is going out of this body, how much is of this emission is actually reaching the second body? Suppose we call this body body 1 and we call this body 2. So how much of these arrows are actually falling on body 2? If some of this radiation is going out like this, then we can say that all the radiation is not falling on body 2. So the fraction of radiation that goes out from body 1 and falls on body 2, this is known as what we call the view factor. So what is view factor is defined as how well one surface can see the other surface. So view factor, we always write it with a letter F with a subscript. The subscript is written as Ij. When I say Ij, it means that whatever the radiation is going out of the body I and it is being intercepted by the body J. That means it's falling on the body J. This is the fraction of the total radiant energy that is emitted by surface I, which is intercepted by surface J. That means this is the, if you suppose you look at the arrows, you will see that this arrow, this one, and this one, they fall on this body 2. However, this arrow and the last two arrows out here, they do not fall on body 2. So the entire radiation that is given out by this first body is not falling on the second body, only a fraction of it is. And this fraction is given by the view factor. You know, a diffuse radiation, if you remember, I had told you about diffuse radiation and spectral radiation. In the case of diffuse radiation, the radiating surface, they emit radiation in all directions so that the radiation emitted may not fall on another surface in the ground. They cannot fall on another surface. This radiation is intercepted by the surface J and will be fully absorbed if the J is a black body. Otherwise, it will be partially absorbed and the rest reflected or transmitted. So what does this mean? What I'm trying to say is that whatever radiation goes out of the body 1 and is falling on body 2, if body 2 is a black body, it will absorb all this radiation. If body 2 is not a black body, then part of this radiation can be reflected back, part of it can be transmitted through it, all kinds of things are possible that is there if body 2 is not a black body. Now, it is not just important for a body to, see, when we talk about heat exchange, we're talking about essentially transfer of heat between two bodies. Say, for example, this is my body 1 and this is my body 2. So this is body 1 and this is body 2. So all the radiation that is given out by the body 1, if everything is falling on body 2, then it is one thing. But when body 1 gives off radiation, it will be especially diffuse radiation, just giving it off in all possible direction, and not everything is necessarily falling on body 2. And whatever falls on body 2 also, how much is being absorbed by body 2, that is my view factor. So view factor becomes a very important term when we are talking about exchange of heat between two surfaces. Now let us look at a few small things about the view factor, because we are going to use this a lot. And when we do our problems about exchange of heat due to radiation between two bodies, you will see how this view factor becomes very important. So let us see what we have. Let me just get my pointer again. Okay. So the view factor from a surface to itself will be 0 unless it can see itself. So Fii is 0 for plane and convex surfaces, but not for a concave surface. So let us see what are they trying to say in this. What they're trying to say is that suppose we have a plane surface and radiation is going on. There are 3 blue arrows shown out here showing radiation. So if I drew more arrows also from here, say for example, from here, all these arrows are going out of the plane surface. Nothing is coming back to the plane surface, since all of these arrows are straight lines. So whatever is going out of the straight surface. So whatever radiation is going out from the surface 1, nothing is coming back to surface 1. Everything is going out of surface 1. Maybe it will reach a body 2, a body 3, a body 4, whatever is the case. But when it comes to radiation going out from 1 and falling into 1, nothing is coming back to 1. नीचे तक की तरफ कुछ भी नहीं आ रहा है, because these are all straight arrows which are going outside. So in this case of a plane surface, F11 means the radiation is going out of surface 1 and it is also falling on surface 1. This becomes equal to 0. Now if you look at a convex surface, the curvature is like this. The radiation that is going out of the convex surface is essentially these arrows, blue arrows which are there. So when I have this blue arrow that is there, this is say a surface 2. You will see that everything is going to go out of the surface. The curvature of the body is such that everything, even if something goes out from here, say for example, it will go out, but nothing will come back to it. So we can say that the view factor of radiation going out from body 2 and coming back to body 2 is equal to 0. Nothing is coming back to body 2. Everything is going out. Then comes the concave surface. If you look at the concave surface, which we call, say, surface 3, then this arrow shows whatever is coming, radiation going out from here, it is going in this particular direction. Whereas this second one, which is there, it is coming in a straight line and hitting this surface. That means it is touching, it is coming out of surface 3, and it is also touching surface 3. The same here, it is coming out of surface 3 and is also touching surface 3. So for a concave surface, this amount of radiation going out from 3 and falling on 3 is not equal to 0. That is why it is written as not equal to 0. It is some value. How do we find out how much of it is it? That is something we will figure out as we go on studying, but it is not directly on that same body. The view factor ranges from 0 to 1. So the 0 is the worst possible case. That means nothing is coming back to it. And 1 is that everything that is given out by the body is coming back to the body. We will see some more examples and you will understand this better. So Fij equal to 0 means two surfaces that do not have a direct view of each other. That means if there are two surfaces, one of which is not falling on the other, then this is called the, this is represented by Fij is equal to 0. And Fij equal to 1 means that the entire radiation emitted by I is intercepted by J. For example, when is that possible? Let's see. These are two spheres. One is called the inner sphere and one is called the outer sphere. So the inner sphere will give off radiation, just like blue arrows are showing, but it will also give off radiation from this side, this ones that I'm showing right now, that we can be giving off radiation in all possible directions. But if this inner sphere is inside the outer sphere, no matter what kind of radiation is given out, in whatever direction it is given out, it will definitely be intercepted by the outer sphere. Outer sphere पे ही जाके गिरेगा और कहीं जाने की जगह ही नहीं है. और बाहर कहीं निकलने की, because there are no holes out here, so nothing can escape. So whatever comes out of the inner sphere essentially falls on the outer sphere. So that is why we can say that F12, that means coming out from 1, falling on 2 is equal to 1, because there is no other possibility that can happen. Whatever is coming out of 1 will not fall on 1. The only place it can go to is it can go to the surface 2. So this is a case where you have Fij equal to 1. Ij stands for, say I stands for surface 1 and J stands for surface 2. So this can be given as Fij or F12 is equal to 1. Now, there are some relationships to understand this view factor. And we will try to understand these relationships by certain rules. And these rules are known as the reciprocity rules. So let us see what there are different rules. The reciprocity rule, summation rule. We will try to understand each of them one by one. So let us first look at the first rule, that is the reciprocity rule. Let me get my pen again. This is my, just a moment. This is my reciprocity rule. What is this? Now suppose we have two bodies, A1 and A2. Radiation going out of A1 is falling on A2. Both of these bodies, if you notice, I have written, are black bodies. So the energy leaving surface 1 and reaching surface 2 is equal to EB1A1 multiplied by the view factor F12. What is EB1? It is the total emissive power of the black body multiplied by the area multiplied by the view factor. And there will be radiation which is given out by body 2, and that is also falling on body 1. In that case, what will it be? It will be EB2 because it is coming from body 2 into A2, the area of the second one. And now if you notice the view factor, it is F21. F21 means the radiation that is coming out from 2 and falling on 1. So the first letter denotes kahan se aa raha hai, and the second letter denotes kahan tak pahunch raha hai. So these are the two values. So this is 1 to 2 means going from 1 falling on 2. 2 to 1 means it is coming from 2 and falling on 1. Since the surfaces are all black and the incident radiation is absorbed, the net rate of heat exchange, that is Q12, is given as the difference between the two of them. That is EB1A1 F12 minus EB2A2 F21. This is the net rate of heat exchange between the two bodies. Now, if the two bodies are at the same temperature, that means if this is at a temperature T and the second one is also at a temperature T, then what will happen, that because they're at the same temperature, there will be no rate of heat exchange. So Q12 in that case will become equal to 0. So when T1 is equal to T2, and you know EB1 will be equal to EB2. Why is that? Because EB1 is essentially means this EB1, say for example, if I write that what is EB1, if you still remember, EB1 is sigma into T1 to the power 4. T1 to the power 4. And EB2 will be sigma T2 to the power 4. But if T1 and T2 are the same, then EB1 and EB2 are the same. So if putting this expression that Q12 is equal to 0, that means this becomes essentially equal to 0. And using the fact that EB1 is equal to EB2, we get that A1 into F12 is equal to A2 into F21. So area of 1 into the view factor going from F1 to 2. Second one is A2 is the area going from 2 to 1. The net heat exchange that is given out, now we can see, if you look at this expression of net heat exchange, now since A12 is A1 into F12 is equal to A2 into F21, we can take that as common. So A1 into F12 is common, EB1 minus EB2. Or you can write it as A2 and F21 because they're the same thing. We can either write it in terms of A1 or we can write it in terms of A2. जब problems करेंगे, then you will see कि कौन सा लिखेंगे will depend on what is the data that is available to me. So this is A1 F12 is equal to A2 F21. So this is the same thing, and in brackets we have EB1 minus EB2, and EB1 is given by sigma T1 to the power 4 and EB2 will be given by sigma T2 to the power 4. So writing a general reciprocity rule, I can write that AI Fij is equal to Aj Fji. So if we just replace 1 by I and 2 by j, that is what we get. AI Fij is equal to Aj into Fji. Even though we have started off by saying that all of the surfaces are black, that means this has been derived for black bodies. Even though that has been done, but it is seen that this reciprocity rule also holds for other surfaces which are non-black surfaces, as long as the radiation is diffuse radiation. That means there is radiation in all possible directions. In that case, this kind of representation or this kind of relationship can be used for even non-black bodies. Now look at it. This is the next kind of rule that we are talking about. This is called the summation rule. In the case of a summation rule, what happens is that the radiation leaving any surface of an enclosure must be intercepted completely by the surface of the enclosure. What do I mean? Suppose I have a square like this. This is an enclosed surface. So whatever is given out from here is essentially intercepted by all the surfaces, which the enclosed surfaces which are there. Now, if you're looking at a square, there are four possibilities. This radiation that is coming out from, say, surface 1 can fall back on surface 1, or it can fall on surface 2, or it can fall on surface 3, or it can fall on surface 4. So these are the possibilities. In this figure that I have shown you, there are 6 surfaces. So whatever radiation is coming out of surface 1, one possibility is that it can fall on itself. Other possibility is that it can fall on 2, or it can fall on 3, or it can fall on surface 4, 5, and then 6. Summation rule tells us that the sum of the view factors from a surface I of an enclosure to all surfaces, including itself, must be equal to unity. Because this is a very simple thing to understand. Suppose we have radiation coming out of it. Enclosed surface, that means it is closed everywhere, it cannot go out. So where will the radiation go? Either it will fall on surface 2, 3, 4, 5, or 6. So that is exactly what we are talking about. So suppose we talk about this case where we have 6 surfaces, then we can write that F11 plus F12 plus F13 plus F14 plus F15 plus F16. This is equal to 1. So suppose we are writing it for the square, it will be F11 plus F12 plus F13 plus F14, that is equal to 1. So this rule essentially is known as the summation rule, because we are summing things up. That is why it is called the summation rule. Any questions till now? Can anybody answer, please? I cannot hear anyone.
मैम
एक एक करके बोलो प्लीज.
मैम एफ की नोटेशन बता दीजिए एक बार.
किसकी नोटेशन? एफ की नोटेशन.
एफ
ओके. एफ इज एसेंशियली, एफ का मतलब होता है व्यू फैक्टर. व्यू फैक्टर इज गिवन बाय एफ. नाउ सपोज वी हैव अ बॉडी 1 like this, say for example, and there is another body 2. If the radiation is going out from body 1 and falling on body 2, and we're trying to calculate the view factor, then that view factor will be given as F12. मतलब जहां से निकल रहा है, that is written first, और जहां पे पहुंच रहा है, that is written as second. Now suppose we are talking about the radiation that is going out from 2 and falling on body 1. In that case, my view factor will be written as जहां से निकल रहा है, that is body 2, और जहां तक पहुंच रहा है, that is body 1. So that is the notation of the view factor. Whatever it is going, the radiation is going out from, that is written as first, and the surface it is reaching, or the body it is reaching, that is written as the second one, which is number 2, whatever one it is. So F21 means you immediately know that this radiation is going out from body 2 and it is reaching body 1. And whereas if you have the other way around, that you immediately know that it is going out from body 1 and it is reaching body 2. Is that clear now? Okay. So let us do a little couple of small problems to understand this view factor. So look at this situation, what we have. For the enclosure formed between 2 concentric circles. That means there are 2 circles. One is this circle, which is given by the area A1, the black one. And one is this red circle, which is outside, which is given by the area equal to A2. These 2 circles are concentric. Concentric means they both have the same center. मतलब ये जो center है वो दोनों के लिए same है. And you are told that there is a relationship that R2 is equal to 2R1. So इसका radius अगर हम ले ले, this will be R1. और अगर ये बाहर वाले का radius हम ले ले, this is equal to a capital R2. But there's a relationship between R1 and R2, that R2 is equal to 2 times R1. Find the radiation leaving surface A2 that strikes itself. That means whatever is going out of surface A2 and how much of it is, say, for example, the radiation which is going out of surface A2. Let me change the color of my ink so that it be easier for you to figure out. Just hold on. Okay. Now, if I say that the radiation that is going out of A2, some of it will fall on A1. This one will also say fall on A1. Part of it will go curved like this and fall on surface 2 again. Part of it will go like this and fall here. Part of it will come out here. So part of it will go there. Another part is going to go here. So there are all kinds. So that means part of the radiation that goes out from the outer wall or the outer sphere will fall on sphere 1, and part of it will fall on itself. So this is what we have to find out. What is the view factor of point 2 falling on itself? So how will we do that? Now let us see this. Remember, these are concentric circles. So again, if I calculate or try to look at the in my color, whatever radiation is going out of surface 1, just imagine, which direction mein jayega? This is the direction in which it will go. So any direction it goes, whatever it is, where is it going? It is going and falling on surface 2. Whatever is coming out and falling on surface 2. Nothing is falling on itself. जैसे यहाँ के एक possibility था, for surface 2 से radiation जो निकल रहा है वो दूसरे point पे जाके surface 2 के ही दूसरे point पे जा रहा है. But in case of surface 1, जो green arrow से हम दिखा रहे हैं, that is not possible. Whatever is coming out of surface 1 is falling on surface 2. As the radiation leaving surface 1 strikes surface 2, that means inner sphere की radiation पूरा की पूरा ही outer sphere में जाके अटक जाता है, or it can hit the outer sphere, you can say that F12 is equal to 1. So we have F12 here equal to 1. Why? Because everything that is coming out of all the radiation that is coming out of sphere 1, as shown by the green arrows, are falling on the circle of outside, which is essentially the outer sphere having a, which is called the body 2. So F12 is equal to 1. Again, whatever is coming out of surface 1 cannot fall on itself. So we can also say that F11 is equal to 0. From the reciprocity rule, since there are two surfaces out here, Ij, what we had said is Ai, Fij is equal to Fj into, Aj into Fji. So Ij को 1 and 2 अगर लिखे, so this comes out to be A1 F12 is equal to A2 F21. Now, if I want to find out the value of F21, which is out here, I can write this is equal to A1 F12 divided by A2 F21. Sorry, A1 F12 divided by A2. F21 is what we are trying to find out. Now, A1 kya hai? A1 is the inner circle. What is the surface area of that circle? Surface area of that circle is 4 pi R1 square. Then we have the A2. A2 is the surface area of the second circle, that is 4 pi R2 square. So these are the ratios of the two areas. Now F12 is what? F12 is the view factor of the radiation that is going from 1 and reaching surface 2, which essentially equals to my value of the value of 1, because we had said that whatever goes out of surface 1 reaches surface 2. Now, if I 4 pi and 4 pi can be cancelled out from here. So what we have is R1 by R2 whole square. So instead of R2, we can now write R1 divided by 2 times R1 square, because you're told that R2 is equal to 2 times R1. So if I now put in the value of F12 as 1, and R and R1 cancels out, and if you square this term, this becomes 1/4. That 1 into 1/4 is equal to 1/4. So F21 is equal to 1/4. Now from the summation rule, I know that, what was summation rule, if you remember? That if something is going to an enclosure, then F21, then all the radiation which is going to all the surfaces along with itself, the summation of that is equal to 1. Now here we are talking about only two surfaces. So F21 and F22, the summation of that is equal to 1. Now F21 का value मुझे मिल गया है. F21 is equal to 1/4. Then F22 is equal to 1 minus 1/4, that is equal to 3/4. F22 is equal to 3/4. That means what essentially? This means that whatever radiation is going out of surface 2, only 1/4 of that is falling on surface 1 and 3/4 of that is falling on itself. This is what it means. Whatever is given out by the outer circle that is there, outer circle, whatever in a emission it gives out, only 1/4 of that falls on surface 2 and 3/4 of that falls in itself. That means कहीं ना कहीं 2 surface के पे ही जाके वो hit कर जाता है. So that is what is known as F22 is equal to 3/4. So in order to find this value, we have used 2 of these properties. One is the reciprocity rule, which we have used out here, and one is the summation property, which we have used out here. So I just taught you these 2 properties and I've shown you how we can use this for our calculations. Now let us look at another example to make it simple. So this example, what does it tell us? That there is a hemisphere, not a sphere, आधा sphere or a hemisphere. It is like a half a sphere and it has got a base which is a circle. Now think about a sphere, उसको बीच में से काट दो, the base will essentially be a circle. So this is a circular plate out here which has got a radius of r. On top of that circular plate, we have got the hemisphere. The circular plate is where body 1, which has got an area of A1, and the hemisphere has got an area of A2, which is the second body. As all the radiation leaving surface 1 strikes surface 2, which is the hemisphere, F12 is equal to 1. So now what are we saying? Let's see. What we said right now is essentially that whatever radiation is given out by this surface 1, इसको और तो कहीं जाने की जगह नहीं है. It essentially everything is going to surface 2. Nothing is falling on itself because it's a flat surface, but everything is falling on surface 2. So the view factor of surface 1, 2 that is going from 1 falling on 2 is equal to 1. From the reciprocity rule, we know that A1 F12 is equal to A2 F21. Area of the circle, which is the base, is pi r square, and the area of the hemisphere is half the area of the sphere, that is 2 pi r square. So now if I want to find out, now I know the value of F12, if I want to find out the value of F21, then what do I do? F21 is equal to A1 by A2 into F12. And I've written out the areas out here. This is the area of the sphere, of the circle, and this is the area of half the sphere or the hemisphere. If I put in these values in the areas, this pi r square cancels out with this pi r square, and what we are left with, 1 into half is equal to half. So F21 is equal to half. Now we know what are the values we know. Let me use another color of pen. So we know the value of F12. I know the value of F21. I know the value of F11. Why is F11 equal to 0? Because this is a flat surface. Anything that is going out of the flat surface has to go outwards. Nothing comes back to itself. So I know F11. I know F12. I know F21. The only thing that is left is F22. So in order to find out F22, we again use the summation rule, that is F21 plus F22 is equal to 0. We have found out the value of F21 out here. So F22 is equal to 1 minus F21, which is half, and F22 also becomes equal to half. In this problem, what were you asked to find out? You're asked to find out the view factors between plane 1 covered by the hemisphere or A2. That means from 1 to 2 जो भी है उसके view factors निकालने थे, but we have calculated everything. We found out F11, we have found out F12, we have found out F22, and we have also found out F21. So we have found out all the possible view factors which are there when we are talking about this kind of a surface that we have. Now, there are a couple of more, two other examples that I would like to do in terms of view factor. But before that, since we're almost running to the end of the class, is there any question about these two small problems that we did? These are questions that are often asked in your gate examinations, etc. So it's very important that you clear your concept about view factors. So any questions about these two small problems that I did?
No, ma'am.
Okay. So I have already sent you all the material, so I'm not going to send you anything anymore. But you can go through, you know exactly how much I have done today. So go through that, and then we will discuss more of this in the next class. I will do two more examples about only this much of the view factor before we go into other variations or other types of calculations of view factors, and hence more on the radiation part. Okay. So what I'll do is I'll stop right out here, sharing out here, and then we can go back to the class.